So we're going to hear the talk from Ralph Philipp Weinmann. All your baseband are belong to us, sort of, the baseband apocalypse, about attacking the GSM software stack from the base station perspective. So please give him a warm round of applause. Welcome.
So I don't need that slide anymore. So I think I should first clarify what this talk is about. So this talk will be about memory corruptions in cellular stacks with a focus on GSM. My focus is on practical attacks, and the aim of these practical attacks is to demonstrate code execution on the baseband processor. Moreover, the focus will be on smartphones. I'll first start with an outline of the talk, so I'll give you motivation why I'm interested in this particular topic and why I think this is a timely thing to research. I'll show you an attack scenario, hopefully with demo. I'll give you market analysis, a GSM smartphone intro for those of you who are not familiar with the architecture here. I'll tell you about baseband security and how to find bugs in baseband stacks, how to do the exploitation, what the impact of these findings is, how the disclosure went, and I'll finish with some conclusions. So, the motivation. Cellular phones usually are in close proximity to their user. Smartphones have become basically personal assistants for many of us here in the room. How many of you still use a PDA, like a regular PDA that doesn't have a cell phone component? Okay, there's some, okay. How many of you use a smartphone instead of, how many of you have used a PDA before and now you're using a smartphone? Okay. So the thing is, this fraction of people will grow because vendors make their phones more and more powerful and smartphones get cheaper and cheaper. At the moment, one of the goals is to make a sub $100 Android phone in the next year. And this should change the market significantly again. So now the problem with this is smartphones have become valuable targets. I mean, they store personal information, but also, in most of the cases, corporate information for those people who work in those environments. And a lot of them also have access to corporate networks because, well, they connect to some email server and have credentials for that, or they have credentials for a virtual private network, or such things. In contrast to feature phones, smartphones for an attacker provide much higher value. Because, I mean, after all, you attack a feature phone, it's some 13-year-old who has like a €10 credit limit, and no important, like, maybe some pictures of her friends. That's not what you're interested in as an attacker. You want to have something where the user can build arbitrary things to his corporation where he actually has valuable information. Thus far, the air interface has been considered as an attack vector in previous talks here at the CCC, for instance at Harald's talk last year. But I haven't seen anybody doing practical exploitation on this yet. And this is what this talk is about, and this is what should change now. So the attack scenario is as follows. You have a fake BTS, so base transceiver station for GSM in this case. So why GSM and not 3GPP? Simple reason, for GSM these have become very cheap. So one of these devices here costs, in the cheapest configuration, about $1,500. And there are other devices between $2,000 and $5,000 that you can buy. which work with other software. So this one works with OpenBTS. There's the IP Access NanoBTS, which works with OpenBSC. Or if you are very lucky, you can still get a Siemens BS11 somewhere, and then this costs about 250 euros back when Harald resold them. Those were old base transceiver stations for GSM. I'll speak about 3GPP at the end. There's some interesting developments there as well. But back to the attack scenario. So what you do is you have such a base transceiver station. You can spoof a network operator now. Maybe the local network operator, maybe some other network operator. And you wait till a target connects to your BTS. If you're clever, you spoof the network in such a way that all the parameters match the cell that the user was previously connected to, and you're just a little bit stronger. Nobody will be the wiser. So this is actually the nice thing about this attack, about this attack vector. If you do it right, it's logless. Because if you do it right, you will not crash the handset, you will execute code on the handset, but without causing any disturbance, except for the things that you want to achieve. And if nobody is in the vicinity with a sniffer, there will be no trace of your attack afterwards. Some of you might have seen Colin's talk about attacking phones with SMS messages or MMS messages. That's nice as well. The problem I see there as an attacker is he leaves logs in the network operator, in the network's operator's network. So this is why I think this is a much nicer scenario for a skilled attacker. So this link between the phone and the base transceiver station is actually bidirectional, so it should be an error on both ends. It's called the UM interface or error interface. I will take away all of the for this talk, useless things that you don't need. So if you look into books about GSM, you'll see much more detail than what is on this slide. But for this talk, this is all that's important. So there's 3 layers on the baseband side that you usually have. There's layer 1, which is the physical layer. Layer 2, which is LAPDM. This is similar basically to Q931 or LAPD in the ISDN world. And above that you have layer 3, which can be subdivided in 3 different sub-layers, namely the radio research layer, the mobility management layer, and the connection management layer. Actually, that should be a CM and not an MM on the top. And the thing is, you need, in this layer 3, you need an established connection on the lower sublayer to have something going on the next sublayer. So you need a radio resource connection to do something mobility management-wise, and for the next layer, the same. Now, let's have a look at smartphone architectures. Smartphone architectures usually look like one of these 2 scenarios. So you either have a so-called application processor, which is basically responsible for drawing all the fancy stuff on your screen, and you have a digital baseband processor. This is responsible for communicating with the network. Why is that, you might ask? So there's a simple reason. As the demands from the operating system vendors for these cell phones grew bigger and bigger, it wasn't sufficient anymore to have just a single CPU. There are other people who also argue that it was the carriers who didn't want to have code running on the same, by the user running on the same processor that the baseband stack was running on. It's not clear to me whether this is actually the case. You can't see this in any literature. So this is just circumstantial evidence or rumors. So okay, so on the left-hand side, you see 2 separate processors which are connected using serial communication or shared memory. A little chunk of shared memory, basically, between these 2. And both of them have their own chunk of RAM. On the right-hand side, you have an application processor and a digital baseband processor that actually share the same RAM. And interestingly enough, what happens, or what happened in design, was that the chip manufacturers decided to make the digital baseband processor the master in this multi-core architecture, or multi-processor architecture, depending on what design we talk about. So you can have these two in the same chip or in the same die, or it can be two dies as well, but nonetheless they can communicate to the same RAM. But in most cases it will be the same chip that communicates with the same RAM. So the left-hand side is called baseband as a modem, and the right-hand side is called shared memory architecture. Now, the next thing that you do as an attacker is, of course, you do some market research because you want to know what's going to pay off to attack, right? So then you see, okay, there's a large chunk of MediaTek devices, there's a large chunk of Qualcomm devices, and there's a large chunk of Texas Instrument devices. And Infineon is like 11%, and ST Ericsson is 10%, so it's a little bit smaller. Okay. But that didn't quite connect with what I had seen in actual smartphones. And this is, in fact, this is the shipment share for all of the phones in the world. So this is like Strategy and Analytics is a company who does these reports, but I've only seen reports for like all of the phones thus far, and not a distinction between the smartphone and the feature phone market. If you look at smartphones, you'll see the following. There's actually not so many baseband vendors anymore. If you look at iPhones, they all have Infineon basebands. If you look at the HTC Android phones, they all are Qualcomm. If you look at the Windows Phone 7 launch phones, they're all Qualcomm as well. Samsung uses Infineon mostly in the smartphone segment. Nokia has their own CPU, which apparently is Texas Instrument design. And BlackBerry either uses Marvell or Qualcomm these days. Okay, so then you look at the security. How we do that, I'll tell you later. But the problem here is the code base for the GSM stacks was created in the 1990s. And the attitude towards security in these software components is from the 90s as well. And to some of you who have been around in those days, you know what fun you could have had. What fun you probably had, sorry. So the thing is, in general, baseband stacks consider the network elements that they communicate with as trusted. This was not a wise, but maybe a somewhat sensible decision back in the 90s when all this equipment costs a lot of money. It's not a sensible decision anymore. I mean, you have to consider that the network elements actually might be malicious. And what's even better is that the people who designed these protocols were very much inspired by ASN1. And as you probably know, there are many length fields in ASN1. There are many length fields in GSM and also in the 3GPP protocols. It's actually surprising because they sometimes prefix fields with a length component, which later in the standard are described as fixed length. And you go like, whoa, what are you doing there? And this actually leads to some nice bugs, as you'll see later. Now, the problem is that at the moment we almost see no exploit mitigations in the stacks. So there are no stack canaries, there's no heap protection, there's no NX, and there's no ASLR. All of these things are standard in desktop operating these days. But the problem is these are embedded devices. So all of these mitigations will cost you performance. Some of them will cost you more performance, some will cost you less. There's one exception. The latest generation of the Infineon baseband chip, the XMM6180, that is used in smartphone, does have an X. So this is the chip that's used in in the iPhone 4 and in a number of new Samsung devices for, I think, the Galaxy Tab as well. But NX has been defeated on these chips. I can't actually tell you why, because I promised people not to. But the thing is, if you look, I wasn't involved in defeating this, but if you look at the iPhone 4 unlock, you will see how it is done, or how it can be done. The other ways around, but this is a very nice one when you see it. Now, where do you look for bugs? I mean, the physical layer, nah, not really. Oh, well, there's some exceptions. There are voice codecs that have length fields, and this can be very funny as well. On layer 2, there are state machines for handling things. There's some bugs, but in general, the messages are too short. So you can crash things, but it's not worthwhile, I found. On layer 3, it gets interesting, because here you have all of these variable length messages. Although you're restricted by 255 octets usually, unless you have things like RLP where the messages themselves are ASN1 encoded again. They can actually be considered above layer 3. And this is solid gold. This is where you find very good bugs. Now, how do you find them? When I first started this, so there's a backstory to this, which I may mention at the end if I have time. People try to talk me into fuzzing, like, you don't have to do a thing, you just run your fuzzer and watch for the, watch your screen, and then there will be results. And I did that. I had many crashes, but I had no way to figure out which one of those were useful. I didn't have that because I don't have source code for the stacks. For vendors, this is a different situation. Vendors can set up a test bed and shake out the low-hanging fruit with fuzzing. But for me, I didn't even know whether it was the same bug that I triggered with a mutated message. So it was static analysis, but the problem is there's no source code, right? There's one exception. There's an Italian phone, the Vitel TSM30. So Vitel was an Italian company that went belly up at some time in the early part of this millennium, and the source code for this handset was available for a number of years. Many people have downloaded it. You can't download it anymore from that SourceForge page, but if you ask around, somebody will have it. So this can be considered more or less in the public domain. I mean, it has been available for 4 or 5 years from a SourceForge page. It's not actually useful for finding bugs in any of the modern smartphones, except for the fact that it tells you how these things are generally programmed. Because, I mean, come on, how many of you have coded it? Okay, this is going to be an interesting. How many of you have coded a cellular stack in this room? Oh, okay. Okay, so I hadn't. So I didn't even know how you, like, I mean, we're looking at the standards, there's some things I could see that there would be natural ways to do them, but this was a very valuable thing to look at to understand how you'd generally go about these things, and it turns out that basically all of them are the same. Different implementations, but the same general principle. But the conclusion was, well, you have to reverse engineer binaries to get somewhere. So the problem is, where do you get the binaries? So one of the sources for the binaries, of course, is firmware updates. The other option is, if you are lucky, you can attach a JTAG interface to your phone and not brick it. And in that case, you might be able to dump the memory, the flash memory, and sometimes the RAM. However, this oftentimes is not possible for newer phones. There's an exception. HTC phones seem to be very nice for JTAGing. So for me, it was firmware updates, and later on, I also had the ability on iPhones to dump memory through bugs in the AT command parser. So these are the bugs that are used by the iPhone dev team to produce the unlocks, but they can also be used for other things. So you can dump RAM or flash memory. You don't need to dump flash memory, but it's useful to be able to peek into the RAM to figure out whether the heap actually is at the address that you think it is. Also to get like the MMU configuration. So with firmware updates. Firmware updates often contain the baseband firmware as well. That's the one we're looking for, but it's packed multiple times usually. But there are tools for extracting that. And nicely enough, for Qualcomm, what you'll end up with is just basically an ELF file with a loader. You can strip the loader from that, and then you can just load that into IDA and analyze it. For Infineon, you need a custom loader relocator. This is something called a scatter loader. This took me actually a while and help from the iPhone dev team to figure out. But I think there now is even a tutorial by Ilfaq on how to deal with those things, because it's basically these scatter loaders are very common in the ARM world. Now, it looks like I have the wrong slide as the next slide, but I'll talk about it anyway. We'll do a quick detour. So, can we do that, or should I skip ahead to the? No, I'll skip ahead. Okay. So for reverse engineering, IDA Pro is mandatory. What was very helpful for me initially was I took the ARM compiler runtimes and used bindiff, which is a tool by the company Dynamics, and ported the symbols for the compiler runtime to the binary I had. So this means that you instantly are able to locate things like memcopy, string copy, sprintf, and such things, and the binary looks much nicer to you. You can also identify memory transfers in the binary using scripts. So there are scripts you can write for binnavi, which is another tool by Dynamics, and on an intermediate language, you can identify all of the memory transfers in the binary. And if you have those, you can intersect a set of these memory transfers with a set of the functions that actually touch packets that come from the air interface. And henceforth, you can analyze all of the interesting locations where things could go wrong, like where an unchecked memory transfer could occur. It's very nice that the vendors left many strings and assertions in the binaries. So except for one handset vendor, you'll always be able to find basically the source code file name and the line numbers certain things happened on, and sometimes error messages why things did not work. This allows you to quickly identify what section you're in, because the thing is, these things are not randomly linked. I mean, there's not some permutation, there's no obfuscation going on. So you'll have very clean-cut segments in your binary for things like the radio resource and for the mobility management and the AT command parser. And by knowing this, you can concentrate on the things that you're interested in. So there's one step that you have to do before you can actually find good bugs and exploit them. And this is a hard one. So the problem is that in principle, all of these stacks pass around the messages from layer to layer using message passing. So you'll have different tasks that interface with each other using a structure. So they'll send around a message through this message passing interface, and you have to be able to at least understand parts of this structure to figure out where a message is flowing. You don't need to fully reverse these data structures, But this is a part that you can really sink time into. But again, the assertions are very helpful for figuring out where the actual points are that do the message passing. Okay. So these were my initial targets, because I had these when I started. So I had an iPhone and I had a Qualcomm and an Qualcomm-based device, an HTC Dream. And I downloaded firmware updates for these and looked into them. And the types of bugs that I found were, there were many, many unchecked memory copies. So this is like the easiest one of these to identify once you have memcopy, of course. There are a lot of objects or structure. I mean, it's not really C++ that these things are coded in, so it's mostly structural lifecycle issues. So these can lead to use after freeze. These can lead to uninitialized variables, also to confusions in the state engine, meaning that, for instance, you have a 5-step state engine that should be run through in its predefined order according to the standard, but you just hop into the 3rd state without going through the other ones. This is possible in some of the stacks, and what it usually leads to is that there are variables that, or usually static variables, that are not initialized yet or that are still set to the old values that are then used by the state engine. This is somewhat tricky to exploit, but it's, these are nice bugs. Also, there's something that I call protocol foobars, where you actually have code paths that should only be reachable through a UMTS message that can also be reached through a GSM message. So this is, for instance, if you have an information element in a GSM message that is for UMTS. I was later told that these, what I call protocol foobars, are actually features, because you need to handle you need to handle these messages if you support both UMTS and 3GPP. Because what happens if you started on a UMTS connection and you go outside of your cell and you are handed over into a GSM cell, then you're still getting those 3GPP messages. And the first bug I found in the Qualcomm stack was of this kind. This is actually a very powerful bug because it's very, very simple to trigger and it's very simple to exploit. And it's surprising that to me it's surprising that nobody has found this before. So as you probably all know, GSM and UMTS use a challenge response authentication. Now, for GSM, this is a one-sided authentication. For UMTS, it's a mutual authentication. So in GSM, they used a fixed length message, 16 bytes rand, and a 4-byte result that was sent back from the handset for the authentication. In 3GPP, they were like, oh, well, yeah, we still need those 128-bit queries, but maybe we need longer or shorter messages in the future. So they added variable length challenges called the auth-end challenges. And later on the standard they write, but these are always 16 bytes long. And you go like, yeah, what are you doing there? And this is functionality that is not needed in GSM, but you can trigger using a GSM base station. So if you have a GSM BTS and you do an authentication, you send out an authentication challenge, you can actually have both the information element for the rand and for the auth-end in it, and it'll trigger this bug, and you'll have a very easy stack overflow. What will happen is that you'll get direct control over the code, over the execution flow. So Qualcomm fixed this bug now. It has been pushed to the OEMs. I understand that all of the Windows Phone 7 handsets have been patched against this bug, but I haven't seen it anywhere else yet. So the bug fix. So it's not quite clear to me what incentive you need or what pressure you need on the handset vendors to fix these bugs. For the second bug, it's somewhat better because it's fixed in all of the basebands of the latest iOS firmware. So this was a similar bug again. So there's this temporary mobile station identifier, and this is a 32-bit entity. It's always 4 bytes long. It's everywhere in the standards, it's 4 bytes. But it's encoded as tag length value. I don't know why. And some clever engineer in the company that provided Infineon with the baseband stack decided to use the lengths that came over the air interface for copying around the TIMSI in the location update and in other places as well. So this results in a heap overflow. This is harder. I mean, it's as easy to trigger as the last bug, but it's harder to exploit. So for this one, you actually need to, I think I need 5 messages to pull this off, and it's not really, it's like 65% stability at the moment. Because you first need to allocate an area of a certain size, then you need to deallocate something. So you need to allocate a second area, you need to deallocate something to make a whole, and then only with the next allocation you have the right setup, and then you can only then you can exploit it. As I said, this was fixed in the iOS 4.2.1 update, but here's an interesting question. All of the unlockers usually are not at the latest baseband. So although in principle all of the iPhone users that do not use the original iPhone should be patched, those of you who depend on the unlock will not be patched against this. I will now go back to the slide that I skipped over earlier because this is something. I'm sorry for the nonlinearity. There's something important as well. You can identify the software version running on the device over the air. Why is that? So most of you in this room probably know the IMEI of the handset. This is the International Mobile Equipment Identifier. This is just like the thing that makes your handset unique, except if you're in India, then you all have the same IMEI. This usually it's a type approval code plus a serial number. And from the type approval code, you can deduce which manufacturer made the handset and which model it is. Now, at a later point in time, they decided to add another field of 2 bytes to this IMEI, and this is the new IMEI SV. And this is the IMEI plus software version. And this basically identifies your baseband version. It should identify it uniquely, it's not always the case, but it's a very good indication for figuring out what handset you're running against, the IMEI, and this is a very good indication for figuring out which particular baseband revision you are running against. And it can be queried from the BTS. And actually the test network that's operated here now queries not only the IMEI, but the IMEI SV as well, because we want to have some I want to have some statistics on how many different, and whether anybody of you upgraded during the CCC. So that's one identification you're interested in, but there's another identification that you're interested in as the attacker. Namely, you have a phone number, but you also want, I mean, the victim is going to register to your BTS using the IMSI. But you can resolve the phone number to the IMSI using services like route to messaging. So this is just like an HLR query. There are operators who have blocked this now, so I'm not able to do this for T-Mobile, USA, and AT&T anymore. But there are other ways as well that you can use to figure out what cellular number a user has. So one of them is there are a number of info leaks that allow you to extract the mobile number directly. So basically, an information leak, which sends you a piece of the memory of the baseband over the air. And if you know, like, this is the software version that I'm running against, you know where in the memory the number of the subscriber is stored, and you just can send a message that triggers an information leak, and then you get 16 bytes out of it, and you get the number back. Okay, sorry. Skip over that again. So, I have a little demo, hopefully, for you now, but a word about clocks. If you do this, you should always get a good clock. I have had very many troubles because of this. The clock that's inside of the stock USRP is not good. It's first of all, it's a 64 megahertz clock, and in GSM, you need to derive the symbol rate from a 13 megahertz clock, and you see, I mean, 64 and 13, they don't have a common divisor that is greater than 1. And the second thing is, it's really imprecise. It's just a quartz, and it usually has like, in the USRP that I bought for the University of Luxembourg, the clock drift sometimes was up to 50, sorry, not 50, it was 500 ppm. And the GSM spec requires you to have about 0.05 ppm, which is 50 hertz if you're in the 900 megahertz band, and 25 if you're in the 1800 megahertz band. So what I did, I first used a so-called FASI1, that's by a German magazine, because people on the mailing list recommended that. I actually recommended that to people as well. I don't recommend it anymore. Please pay attention to this. The output voltage of this thing is TTL level, and the USRP only wants 1 volt peak to peak. So you're actually operating the thing with 5 times the voltage. I'm not sure whether this is why I burned one USRP, but it's a possibility. So I advise against using this device at the moment, unless you know how to reduce the voltage before you use it as an input. Also, it's not optimal. It's like 20 ppm uncalibrated. You can get it to 1 ppm calibrated, but then you have to make sure that you don't change the temperature in the room. So, a clock tamer, it's done by some Russian people, by a company called Fairwaves, Alexander Chemeris, is a much better thing. I first saw that by a couple of people in Seattle, and I saw how painless things can be if you have the right equipment. Mine currently is stuck in mail routing in Moscow still. So, but this is a much better choice. If you don't, so at the university, I have like a 4,000 euro clock generator, but you can't drag that around. I mean, this is like 10 kilograms. I'm not like touring with this thing.
You can build temperature compensation for the fuzzy.
Okay.
It works also relatively well.
Okay. Well, I haven't. I'm not an electrical engineer, so that's probably also why I shoot myself in the foot with these things. Okay, but back to the topic. So baseband exploitation. When I first started, I had many questions that you probably also have. I mean, what operating system is running on these things? So on old iPhones, it's usually Nucleus. On the iPhone 4, it's ThreadX. It's probably for licensing reasons. I guess ThreadX is cheaper. I'm not sure why they changed it. If you look at the Samsung stacks, they are exactly the same, except they run on Nucleus. Only the iPhone 4 runs on ThreadX. So it's a choice that was made by Apple, not by Infineon. On Qualcomm, it's AMSS, which is a proprietary operating system by Qualcomm. And on new phones, this runs on a so-called OKL4 kernel. So this is an L4 microkernel by a company called, the L4 microkernel, some of you probably are familiar with, but this has been forked by a company called OK Labs, and they sell that to a lot of smartphone manufacturers. And I think one of their goals is also to virtualize, so you can run actually the baseband and the application side on the same CPU again with a hypervisor. The second question I had, I need to somehow locate the buffers for the L3 messages. This is not always easy, but if you're able to use these AT command, exploit these AT command part of the box that I spoke about earlier, this makes locating the buffers much easier. And then for a demo, you have the two options. Do you write new code or do you use existing code? And this choice was made much easier for me after I accidentally, you will not believe this, but this was accidentally, I accidentally eavesdropped or had my girlfriend eavesdrop on me during a wedding of a friend of mine because I switched on the auto answer in the iPhone, because there's a command sequence on the iPhone, and I switched this on by accident, and my girlfriend called, and I didn't notice, and she later called again. She was like, "Hey, I was hearing all of the voices in that room you were in, and I listened to it for like 10 minutes, but you weren't answering. Like, why did you?" So yes, after that, I was like, "Oh, there's auto answer in this baseband. I should find it." And this is present in both the Infineon and the Qualcomm stacks. But the thing is, if you write exploits for this, debugging is hard, and I strongly advise you to either write your own debugger or use JTAG if it's available. So I didn't do that, and I'm still mad about that. So my personal preference for exploitation is OpenBTS because it's cheap hardware and I can modify the software easily. I don't need a Siemens BS11 or a Nano BTS. Also, when I started, I thought that OpenBTS gives me greater flexibility in creating the messages. It now turns out that I think I can do all of the things I want to do with OpenBSC as well. So I could have saved myself some pain here as well. Nonetheless, OpenBTS really is great for one feature, namely, there's a test, most people don't know this, but there's a test call command from OpenBTS to 6 onwards. And if you use this test call command, it's basically a test call to an IMSI plus the duration you want this test call to last. It opens a channel, a so-called SDCCH, and you can inject raw L3 messages to the phone and get them like raw L3 messages back. And this means you can test and exploit all these things without much pain if you have the OpenBTS setup working. OpenBSC is an alternative. And actually, one thing I'd like to do, so there's one problem with the demo. So if I demo here, there's the chance that someone will sniff the exploit, right? So there's a very good chance. So there's two options. Either I try not to demo, or I don't care about it. So I've decided not to care about it. And this also means, wait. This also means that if this demo fails, it has failed a number of times for hardware reasons in the past, or because I'm too stupid to operate OpenBTS properly. What I'd like to do, and I still have to ask Harald about this, is to basically offer people who are on the other network to inject these messages if they want to. So to basically get your, maybe we can, I have to discuss this with Harald first, but I'm willing to give basically the L3 messages to Harald for a test your phone service. And I hope, so the thing is, Infineon and Qualcomm and Apple have been great about patching these things. So it's patched in the chip, on the baseband chip manufacturer side, and for Apple because they have control of the handsets. I haven't seen these patches for the other for the other devices, and I'd like to encourage the vendors to speed up this process a little bit, and hopefully this will be the necessary pressure. Okay, now more about this ATS0 feature, because you're going to need that information if you decide to test this against an Apple device. So you will want to write down this command to turn off auto answer. Because if you test this, what I'll do, I'll turn on auto answer on your phone. So why I demonstrate using that is I don't have to write any code for this. For the Qualcomm stacks, I can just jump to a little piece of code that sets the register to the value 1. So it loads R0 with the value 1. And then I jump into the handler that sets this, for basically for the AT command parser. And for Infineon, it can crash afterwards. For Qualcomm, because for Infineon it will be stored in NVRAM. For Qualcomm, the thing is that you have to continue execution afterwards because it's only in RAM, but it's trivial as well. I will not do the thing at the bottom. So you can make auto answer silent by crashing the communication task between the two sides, but that's really evil. I mean, I want this to be a demonstration, not a fully weaponized exploit. Because, I mean, why I called this, I mean, as I understand, I didn't forge this expression baseband apocalypse. I don't know who did. I heard this first in the CCC Berlin, and I found it a very fitting expression, and I think we're approaching this apocalypse at the moment. I hope I haven't done too much to push. But, I mean, what's the worst scenario that you can think about? So, you can place fake BTS. I mean, it's not big. It's like this. I mean, you can carry this around in your backpack. You can place this in crowded and sensitive areas near the European Commission or near an airport lounge or in the financial district or near embassies. And if you're evil, if you're really evil, you write code. You don't do this demo stuff, right? So what you do is you record audio continuously. I mean, you have memory. So I think on the iPhone 4 I had over 4 megabytes of memory that was free that I could have recorded audio to. If I compress as well, this will last me for a couple of hours, and I can just keep it in RAM. When the next outgoing data connection is initiated by the user, I just piggyback onto that, and I will exfiltrate all of the data. It's nice that they have crypto routines in the baseband as well for various reasons, so I can actually encrypt all of that stuff that I exfiltrate. And in some of the phones, it's not only the microphone that hangs off the baseband chip, it's also the camera. So if you want to get really creative, that's it's your turn then. Now, with shared memory architectures, it's worse, because on a shared memory architecture, if you compromise the baseband CPU, it's game over. You can do whatever you want on the application side to secure things, it's worthless. And I think that's also why Microsoft was so very concerned when I first reported those bugs to them, because I later found out that all of the Windows 7 launch phones are Qualcomm devices, and they all have shared memory architecture. So, yeah, but I didn't know that back then. And at that point, you just place your backdoor rootkit and you're done. But, I mean, these are some. There are other scenarios, which are not on these slides, that I will briefly mention, that really scare the shit out of me. How many of you have seen that BMW and Porsche have something called remote assistance for the driver? So guess how this works? Do I need to tell? So it's usually a module, a 3G, GSM or 3GPP module, that directly connects to your CAN bus. Now, this is, well, I mean, you know, I had a little RC car when I was a child. Now you can have many big RC cars. But don't do it, please. So let me just make things perfectly clear. I really want these bugs to be fixed. Like, there are bugs where I think that, okay, someone found it, someone didn't disclose it, so what? It's just one in like many bugs. The same is the situation here, but in my opinion, phones have become components of our daily life that we very much depend on. And I think we will depend on them much more than on computers in the future. And I'd like for these devices to be at least somewhat secure. So we need to push people to make them more secure. And that's why I pursue something I call incentivizing disclosure. So when I looked at this, I did not find just these two vulnerabilities. But basically, you have to multiply the number of vulnerabilities that you saw by a low two-digit number. And I don't want to give them all of the vendor directly, because if I do that, he'll fix all of them, but he will not look for more. So what I've done is I have showed these two bugs to Infineon and Qualcomm, and they have believed that, yes, indeed, they do have a problem. And they now perform their own audits, or in some cases, I understand that one of them at least has performed a full audit already. And they have found, let me just calculate, I think almost 7 times as many bugs as I had on my stack. So now the time has come to compare results. So basically what I do is now I'm in the stage I have disclosed the bugs, vendors have looked at it, we compare results. I think the strategy has worked thus far. I'm not sure whether it'll always work. There have been other unaffected vendors who are like, oh, this is not exploitable on our CPUs because we have stack canaries that we check between process switches. I'm like, well, how does that help you? But the thing is, it seems to be necessary to demonstrate this to get it fixed. And it'll only get worse with UMTS, because UMTS uses mutual authentication, but there's something called the radio resource control layer, which is basically the continuation of the radio resource layer you had in GSM. But this is needed for authentication, And it's 1,800 pages of PER encoded. So it's 1,800 pages of specification, and all of this is PR encoded. And this needs to be handled. So there needs to be code written for handling these messages that are specified on these 1,800 pages. And as some of you may know, femtocells are not that expensive anymore. You can buy a Vodafone Sure Signal for, I think, £50 on eBay in Great Britain. And these will become great attack platforms. So, and what I've said about these cross-protocol things, you can also send GSM messages over these femtocells over a UMTS link to the phone, of course. So you have a cheaper attack platform using a femtocell than using OpenBTS. It's still work that needs to be done to make them speak to allow you to speak RSC directly. But I think someone will do, probably someone in this room will do it within the next year or so, and in the next Congress, we'll see femtocells as very cheap attack platforms. So with this, I'd like to cut over to the demo. I understand I have 5 minutes left. And I will first start with the one for the okay, so you will see a test SIM network, and if you have an HTC phone, you should please try connecting to that network. If you have, well, okay, if you want to, of course. So I'm not forcing anyone here. Okay, I have some victims. So, oh, right, now we have the problem. IMSI 2624-202221539103. Okay to attack? Okay. No, I can't. Okay. I'll just try attacking all of you. So, if this doesn't work, your handset will reboot. Maybe I can paste this to the other screen somehow. Wait a second. The last 3 digits of the IMSI are 103. Or can like a volunteer from the audience? What are the last 3 digits of the IMSI? I don't see that, unfortunately. 457, okay. 457. Okay. What phone is it? Okay. Oh, okay. Okay, we have a test call. Okay. Sorry, my OpenBTS just crashed. Who was that? Okay. Okay. How many more minutes do you have at the moment? 0. Okay. Okay, just a second. If I only have a couple of minutes, rather than doing the demo, I'd like to just show you the exploit directly. You will hopefully get the chance to demo it against yourself using the test network later. So this is the radio image for the magic. And wait. So I don't see. You can actually search for typos that they. Wait, sorry. Wait, just wait. Legal sequence. Oh, damn it. Okay, third try, hopefully. Okay, right, this is the one I'm looking for. Right. So if you have the decompiler, you can actually turn this. Shit. I think I have the wrong IDB. Sorry, wait a second. I just want to show you the bug in the binary. Okay, here we are. So this is the authentication. This is the routine that actually handles the authentication messages, and this is what you get when you have access to the ARM decompiler for IDA. So what you see here is this is the information element for the auth-n, and this is basically the mem copy that triggers the bug. So what will happen is the information, the contents of the information element will be copied to this pointer auth-n, which is an alias, l-auth-n, which is an alias to auth-n, with the length from the packet. And this function, in turn, is called from a function that has allocated this on the stack here. So this is not really that hard to figure out once you have identified all of the memory copies in the baseband image. And I'll just a quick look of how many of them there are. So you want to automate this task, right? Okay.
You found the adapters from Market.
Yes, okay.
Talk in less than 10 minutes. You need
Okay.
the adapters back.
Okay.